the highly productive waters off Peru once supported one of the most bountiful fisheries in the world. But in 1983, the nutrient-rich upwelling that produced this rich harvest failed, and the fishery crashed. Deprived of the algae on which they feed, the marine iguanas of the Galapagos starved to death. Arid equatorial islands were transformed by rainfall, but their seabird populations disappeared. El Niño had returned. The climatic perturbations known as El Niño seem to occur every 2 to 10 years. The 1982-3 event was one of the most severe on record, and its effects were felt around the world. Large parts of Africa, India, and Australia were ravaged by drought, while the west coast of the Americas was lashed by storms and torrential rain. The 1982-3 event was also the most comprehensively observed so far. The changing patterns of sea surface temperature were recorded by satellite-mounted sensors, and they showed a region of unusually warm water traveling across the Pacific. But why did this happen? At the time, a number of instrumented buoys were moored along the equator and were sending back information about the wind and sea conditions. In addition, large numbers of drifter buoys were launched into the ocean off Peru. Over several months, they were tracked via the Argos satellite as they drifted with the surface currents. You can see the paths of the drifter buoys looking like comet tails. Thin arrows centered on the equator show wind direction. Slightly thicker arrows show current direction. Watch the buoy drifting westwards just north of the equator. As it approaches one of the moorings, it suddenly changes direction with the current. Normally, we'd expect these buoys to move west in the south equatorial current, under the influence of the southeasterly trade winds. But during El Niño, winds become weak and even westerly, and buoys put in off the coast of Peru seem to wander about aimlessly. Other buoys, previously moving westwards, now change direction. So it seems that the weakening of the trade winds allowed warm surface water, normally piled up in the western Pacific, to flow back eastwards across the ocean. But it's not as simple as that. Sea surface temperature affects processes in the atmosphere. Ocean and atmosphere form one system.
Our work proceeds by trying to model this coupled ocean-atmosphere system. And initially we made these models to develop an understanding, but it turned out that the models worked pretty well to make predictions. Now, in order to make a prediction of, let's say, what's going to happen this year, I would have to know the state of the system of the ocean and the atmosphere on January 1st. And in order to do that, in an ideal world, I would have a tremendous amount of data about the ocean and about the atmosphere, and I would be able to put it into this model. But this data, by and large, doesn't exist. What we do have are some relatively scanty observations of the surface winds over the tropical Pacific based on volunteer observers on merchant ships. We need the winds everywhere, and we rely on the people at Florida State to take these very sparse observations and turn them into a map which covers the whole surface of the tropical Pacific. We then take those kind of wind data and use it in an ocean model to create a state of the ocean. Now we have the ocean and the atmosphere, and we can go, and we go forward, and in a good year, when we're lucky, the way the model evolves, with the ocean driving the atmosphere and the atmosphere driving the ocean, mimics what happens in the real world, and so we can make a prediction. Predictions have value, of course, because these are things which affect climate and affect people's lives, but also making a prediction is a way of trying to verify whether the understanding that we think we have about how the system works can actually be translated into equations which you put on a computer, and then when you let this go, it in fact does indeed do what the real world does.
With increasing success at modeling changes in the tropical oceans, oceanographers are now aiming to predict global changes in the World Ocean Circulation Experiment, WOCE for short.
In this experiment, we would be making measurements of the entire world ocean, looking at essentially a snapshot view of the behavior of the ocean during a 5-year period. Crucial to these observations are satellites. Satellites have the ability to make measurements, at least of the surface layer of the ocean, on a nearly daily basis. Also, the observations in all parts of the global ocean, from ships, from moorings, from drifters on the surface of the ocean, and floats in the interior of the ocean. This data set, coupled with extensive satellite observations, will give us for the first time essentially a snapshot view of the behavior of the ocean.
Understanding how the global ocean works is important if we're to forecast climatic change. Pollution of our planet may already be warming the atmosphere, and there's rising concern about what will happen at the poles.
The polar regions of the ocean play a very crucial role in the global climate system. It's in these areas that the ocean heat is lost or vented to the atmosphere. This is heat that was carried into the ocean in the lower latitudes. In the polar regions, as the heat is lost to the atmosphere, the surface water naturally gets denser and it sinks, and it spreads at some level in the ocean into the rest of the world ocean. Even under the equator, if you go deep enough, you'll enter water masses that were formed in the polar regions. This has an effect of cooling the deep waters of the world ocean, and it also has an important climatic effect in removing excess CO2 from the atmosphere. The North Atlantic, in particular, is important in removing excess carbon dioxide from the atmosphere. Perhaps half of the carbon dioxide introduced to the atmosphere has been removed by the ocean, primarily occurring in the Northern Hemisphere in the production of North Atlantic deep water. The Southern Hemisphere polar region may play a smaller role in the carbon dioxide balance, but it is primarily responsible for cooling the deep ocean. Until the advent of satellites in the 1970s, we knew very little about the sea ice cover around Antarctica, other than the northern fringes. The satellites revealed a rather remarkable feature in the Antarctic sea ice, in that there are persistent open water areas even in the middle of winter, when the area should be frozen over. The atmosphere is cold enough to freeze the ocean, and yet in these areas the ice does not form. These are called polynyas. There are two kinds of polynyas. One occurs along the coastline of Antarctica, and it's essentially formed as the strong winds blowing off Antarctica just remove the ice, exposing the ocean. And the ice forms in this now exposed ocean very rapidly, and then is removed by the wind. Within these coastal polynyas, an enormous amount of sea ice could form, and then is removed to the north, dumping enormous amounts of salt into the shelf water, making it very dense and setting up the stage for the deep sinking associated with Antarctic bottom water. The open ocean polynyas were also revealed by the satellite images, and these were even more remarkable and perhaps more unexpected. In these areas, the surface water is convected deep into the ocean, and deep water then comes up to replace it. There are these elongated convection cells which carry the heat of the deep ocean into the surface layer and prevent the formation of ice. These are called sensible heat polynyas in that they're maintained by the sensible heat of the ocean. The most remarkable of the open ocean or sensible heat polynyas occurred in the mid-1970s, what we refer to as the Weddell polynya. An area of about 300,000 square kilometers was ice-free for each winter for 3 consecutive years. The amount of ocean heat that was lost to the atmosphere during the Weddell polynya events in the mid-1970s is absolutely enormous. We have temperature measurements before the polynya event, and we have temperature measurements in the ocean after. The ocean cooled by about 1 degree down to depths of 3,000 meters. An enormous amount of heat was extracted from the ocean. However, though the polynya event is associated with cooling of the ocean, it may not have had a very large impact on the carbon dioxide balance. The speed of the overturning does not allow an equilibrium to be reached between the ocean and the atmosphere CO2 content. And this is probably true throughout the Southern Ocean. It appears that the main extraction of excess CO2 in the atmosphere is accomplished in the northern hemisphere, associated with the North Atlantic deep water, and that in the Southern Ocean's primary role in the global climate system is to very significantly cool the ocean.
But how fast do the deep water masses carry heat and carbon dioxide through the oceans? Fallout from nuclear explosions has provided useful tracers for water masses, especially as the radioactive nuclides are effectively time-coded. Another group of artificial substances which can be used to track water masses are the chlorofluorocarbons, CFCs or freons for short. Water collected from the deep ocean contains gases dissolved in it when it was last at the surface, and the relative proportion of these gases depends on their solubilities and their concentrations in the atmosphere. Denise Smythe-Wright has used the ratio of two CFCs, Freon 11 and Freon 12, to work out when water several kilometers deep in the ocean was last at the surface. The concentrations of Freon 11 and Freon 12 dissolved in surface waters have both increased dramatically since 1950, but not by the same amount. And so measuring their ratio in a seawater sample will tell us how old the water is. This equipment can measure freon concentrations down to just a few parts per trillion. Bubbling inert gas through the sample removes the freons, which are condensed in a cooled coil. When all the CFC gas has been collected, the cooling flask around this coil is replaced with one containing boiling water. The volatile freons quickly evaporate and are analyzed by a gas chromatograph.
These twin peaks on the chromatogram are directly proportional to the amounts of Freon 11 and Freon 12 in the water sample. If we analyse lots of water samples taken at different depths at the same location, we can then plot a graph of concentration versus depth and get a profile that looks something like this. This profile is for samples that I measured just north of South Georgia in the South Atlantic in 1986. The red line represents Freon 11 and the green line Freon 12. There are high concentrations in the top 50 meters, but when we get below the mixed layer, the concentrations become very much less, and the ratio of the two concentrations doesn't change very much. As we go deeper, there is a slight variation at 3,000 meters, which we know corresponds to Antarctic intermediate water. As we go even deeper to 5,000 meters, the concentrations begin to rise again, and the ratio begins to change. If we now look at the curve which shows the freon ratios in surface waters, and look for a ratio of 2, and line this up with the 0-degree curve, because we're working with Antarctic water, which of course is very cold, we can see that a ratio of 2 corresponds to the year 1969. These samples were collected in 1986, so we can calculate that the water is 17 years old. Now we know that Antarctic bottom water is formed here in the Weddell Sea, and the samples I've been talking about were taken here in the South Georgia Basin. So you can see that it has taken 17 years for the water to travel from here to here.
It's not just water sinking into the deep ocean that carries with it information about conditions at the surface. The tiny alga Coccolithus emiliana huxleyi multiplies in the spring, forming enormous milky blooms. On death, their plates disaggregate and rain down onto the sea floor, where they dissolve if the water is deep enough. But scientists at the University of Bristol have discovered that even where sediments contain no skeletal remains, two rather special organic molecules have been preserved. Molecular fossils, if you like. They're very similar, except that one has an extra double bond.
How we stumbled on this was that when we grew some of these algae at Plymouth with our colleagues there, we found that when we grew them at one temperature, then these two molecules were present in a certain ratio. And when we changed the water temperature, then the ratio changed. So we then wondered, could this actually be a sort of thermometer for the water temperature. And we were absolutely amazed when, in going around the ocean floors, we found that indeed these molecules in the sediments showed a relationship to the sea surface temperatures above them at the present day. And what we've done now with colleagues from Germany is to take cores off northwest Africa, say about 20 meters down into the sediment. We sampled them in the lab here and took these small amounts of sediment and examined them for these long chain compounds. And we were extremely excited to see that as we went down this core, back through the last few 100,000 years, we could see our signal of sea surface temperature oscillating about roughly in the same way that it has been found with other methods of getting at the past history of the climate. For example, where the last ice age was taking place in Europe, then we could see the signal of the lower temperatures in the oceans off northwest Africa in the form of this sediment signal. Well, so much for the sea surface temperatures of the past. But we've been looking at our records of the compounds in the sediments even more carefully. And what we've seen in there are molecular fingerprints which do not match those of the marine organisms. So where are they coming from? Well, we've fortunately been able to track them down to the plant waxes which occur on land plants. So what we're seeing here is an input from the land carried on the dusts which are blown in the winds from the Sahara and other regions out into the Atlantic Ocean. So this indeed looks a very exciting new development for us. But anyway, the whole problem we face now is how to do more samples, because we're only looking at intervals in the cores of, say, 1,000 or 2,000 years spacing. We've got to get down to a few hundred years spacing to really see some of the changes in climate that we know go on. How are we going to do this? Well, the only way we can see is to turn to the physicists and the computer experts and to remove the chemical steps from our analytical scheme and use the speed and precision of the newer types of mass spectrometer. We already use autosamplers for gas chromatography, but now we need to bypass chemical steps. One device we are testing is an advanced mass spectrometer system with 3 small mass spectrometers coupled together in series. This device should give us a single analysis in about 5 minutes, rather than 90 as at present, as we don't need to separate the mixtures. We can do the analysis directly. Really detailed molecular records at a spacing of 100 years or less will be necessary to predict the climate change of the future. And we really need that information if we're going to live safely on this planet. Now, geologists have a maxim that the present is key to the past. But what we need to do is to use the past to predict the future.
In the tropical oceans, reef-building corals have been responding to climatic changes for hundreds of years. They act as living tape recorders of the past.
What do we have here on this lab bench? It's 5.5 meters of slices of a coral from Isabella Island in the Galapagos. The remarkable thing about this coral record is that it represents nearly 380 years of continuous coral growth. Now, corals grow under the sea, but we didn't collect this particular specimen there. This specimen came from a reef that was uplifted virtually overnight in 1954 during a volcanic eruption. This photograph, taken several years before the uplift, shows the dark ocean to the left and the gray volcanic land to the right. The arrow shows a small beach. This photograph, taken several years after the uplift, shows the beach now 1 kilometer from the present-day shoreline. This uplift brought with it many large colonies of corals, one of which, this massive colony of Pavona clavis, we sampled and brought back to the lab. So what can we learn about the oceans from these coral slabs? If we look at them carefully, we see faint banding, but we can't count the bands reliably this way. We can see them much better with X-rays. We place the coral slabs on film, illuminate them with X-rays, and when we develop the film, we see band patterns like this. The alternating light and dark bands form as coral growth responds to seasonal changes in water temperature and cloud cover. Each band pair represents 1 year. Thus, we can age date the coral by counting these bands, just as trees can be dated by counting tree rings. We know very precisely the age at the top of the coral when it was uplifted and died. What we've done is counted these bands back through hundreds of years, back to the time when the coral first started growing. And that was in the year 1583. Now, in the bottom part of this coral, the bands are quite widely spaced and are very regular. Now, corals are very sensitive to changes in water temperature, and these regular bands tell us that water temperatures didn't change very much. Now, if we look forward through time, we see regular bands like this occurring through the mid-1600s, 1640, on up into 1660, 1680, still broad regular bands, conditions very conducive to coral growth, into the early 1700s, on up into the mid-1700s, when we see a remarkable change in the character of the growth bands. If you look carefully at this level here, we see 2 dark bands, and in between a growth hiatus. At this point, the coral was extremely stressed. In fact, large parts of this colony died at that time. This tells us water temperatures were changing, and we believe this represents a major El Nino event that occurred in the year 1747. Well, so far, we've just been looking at the record of growth bands in this coral skeleton, but we can acquire a great deal of additional information by sampling the skeleton. And we sample the skeleton using a small drill, and we analyze the powders that we collect for the stable isotope ratios of oxygen. The oxygen isotopic ratios of the coral tell us the water temperature at the time the coral was growing. Now remember, this coral is from the western side of Isabella Island, and at this location, water temperatures are primarily controlled by the upwelling of cold, deep water as the trade winds blow from east to west across the islands. If you look at the oxygen isotopic results and plot them against year of coral growth, we see cooler water temperatures and hence stronger trade winds during the Little Ice Age prior to 1900. The coolest water temperatures occurred near 1700 and 1800 AD, which also correspond to periods of sunspot minima. The period between 1860 and 1900 is especially important. This was a time of very rapid warming at the end of the Little Ice Age. And if we can understand how the climate changed at this time, we're much better able to predict future climatic perturbations as the Earth warms up due to the addition of greenhouse gases.
A rise in sea surface temperature will lead to an increase in the frequency and severity of tropical hurricanes. Parts of the world now outside the hurricane belt may soon experience their destructive power. There will be more El Nino events in the Pacific. Climatic perturbations in general will become more frequent and more severe. There will be more floods and more droughts. All these interrelated events result from the powerful coupling between ocean and atmosphere, which controls our climate.